All right, let's talk about the air we breathe. We spend so much time worrying about what comes out of smokestacks and tailpipes, but what if I told you that some of the most dangerous pollutants aren't actually made on the ground? They're literally created in the sky right above us. We're going to break down that chemistry and get way beyond the headlines to see what's really going on up there.
So let's start with this question. When you think pollution, you probably picture a smokestack, right? Black smoke pouring out. But what if the sky itself is the real factory? That question right there is the key to understanding how modern air pollution actually works.
See, to really get this, you have to understand that pollution isn't just one thing. It really has two very different faces.
I think the easiest way to think about it is like cooking. You've got your primary pollutants, those are the raw ingredients. They're the things that are shot directly into the air from a source. But then you've got secondary pollutants. That's the finished dish, the recipe that's actually cooked up in the atmosphere when those raw ingredients mix together and react, usually with a little help from the sun.
So, what are these raw ingredients? Well, they're the usual suspects. You've got sulfur dioxide from power plants, carbon monoxide and nitrogen oxide from our cars, and hey, even natural stuff, like sea salt that gets sprayed up from the ocean. These are the basic building blocks.
And here's where the cooking starts. Those primary pollutants, they don't just hang around. Oh no, they change. Sulfur dioxide can turn into sulfuric acid. Yep, a main ingredient in acid rain. Nitrogen oxide morphs into nitrogen dioxide, which is way more toxic and a major lung irritant. This atmospheric aftermath is often a whole lot nastier than what we started with.
Okay, so every single pollutant out there, whether it's primary or secondary, it has a life story. So let's follow that journey, from its birth to its end.
And it's a pretty simple story, really. It starts at a source. That's the smokestack or the volcano. Then it travels to a receptor. That could be our lungs, a lake, a building, you name it. And finally, it ends up in a sink, which is where it's finally taken out of the game.
Now that word sink is really important. It's not just some cosmic trash can. It's an active process where the planet actually cleans itself. A great example is acid rain hitting limestone. A chemical reaction happens that turns the liquid acid into a harmless solid, basically locking that pollution away for good. The planet has its own built-in cleanup crew.
So now that we have the basic framework, source, receptor, sink, let's see how this all plays out in the real world. We're going to compare what humans are doing to what nature does all by itself, and the results might just surprise you.
Okay, take carbon monoxide. You'd think we're the main culprits, right? But get this. On a global scale, human activity only accounts for this tiny little sliver, about 6%. A much bigger chunk comes from the natural decay of plants, and then there's this massive piece of the pie, nearly 3/4, that comes from sources we don't really even understand yet.
But, and this is a huge but, here's the real kicker. Even though our global contribution is small, our local impact can be gigantic. The normal background level for CO is just 0.1 part per million. But if you're stuck in rush hour traffic, that number can shoot up to 100 parts per million. That's 1,000 times higher. And that is why city air quality is such a big deal. It's all about concentration.
And we see a kind of similar story with sulfur. Just look at this chart. Natural sources, like volcanoes and oceans, they pump out a massive 125 teragrams of sulfur a year. Now, human industry adds another big chunk on top of that for sure, but it really puts into perspective the incredible scale of the Earth's own chemical cycles.
All right, so we've been talking a lot about these invisible gases. Let's switch gears and talk about something we can often actually see. The haze, the dust, the soot just hanging in the air.
So the sciencey term for this is particulate matter, or PM for short. You might also hear it called aerosols. It's basically just a big mix of tiny solid bits and liquid drops floating around. It could be anything from sea spray to desert dust to smoke. The key thing isn't what it's made of, but just the fact that it's there, suspended in the air we breathe.
But here's where it gets really interesting. Not all of these particles are the same. You've got the bigger ones called supermicron particles. They're made by mechanical stuff like wind kicking up dust. They're kind of heavy, so they fall out of the sky pretty fast. But then you have the really tiny submicron particles. And guess what? They are formed by chemical reactions in the air. They're secondary pollutants. And because they're so tiny and light, they can stay in the air for ages and get deep, deep into our lungs.
And this brings us to our final and maybe most important idea.
We have to stop thinking of the atmosphere as just empty space. It's not. The air itself is a giant, churning chemical reactor.
And the perfect case study for this is photochemical smog. It's the absolute classic example of secondary pollution. You start with primary pollutants from cars like nitrogen oxides, then the sunlight hits them, acts as a catalyst, and kicks off this whole chain reaction that manufactures a brand new cocktail of nasty stuff, like ground-level ozone. The sky is literally cooking up smog.
So look, if you take away just one thing today, let it be this. Pollution isn't static. It's not just the stuff that comes out of a pipe. That's only the beginning of the story. The real action, the truly important part, is what happens next in that giant chemical reactor all around us.
And that really leaves us with one last question to chew on, doesn't it? If the sky is a giant chemical factory and we're the ones dumping in the raw ingredients, what exactly are we choosing to make?